This lecture is going to focus on the force of high-speed wind upon a house. So we have our house here. So this will be a typical residential house dimensions. So we'll say it's a 50-foot width frontage. And then the siding is approximately 2 stories, so 20 feet. Then we have a certain rise of the pitch roof, for which we can use the standard residential rise over run. So we have a rise of 3 per run of 4. So if we use Pythagorean theorem on sides A and B, we can obviously use the 3, 4, 5 rule as well, but we will only need to know the altitude of 3. So then we can estimate about 15 feet of depth to the center point of the roof. So we get 15/14 times 3. This will be a projected rise of 11.25 feet. And then lastly, our angle is just the opposite divided by the adjacent, so that's tangent. And so we just get the inverse tangent of 0.75. And this becomes 36.9, about 37 degrees. So if we approximate the drag coefficient for the roof section greater than or equal to about 45 degrees, it then has approximately the drag coefficient of a cone. So we'll just say it's 0.75. And then the flat surface of the siding will have a drag coefficient of 1.0, just the flat surface. And then we have a drag coefficient of 0.75 on the roof section. So we'll assume the wind is blowing towards the illustrated roof and siding regions. So we just want to get the square footage of both the roof and the flat surface as the projected frontal area, and the angle on the pitched roof will then change the drag coefficient lower than the flat surface or siding. So the siding has a projected frontal area of 1,000 square feet, and the roof has a projected frontal area of 562.5 square feet. So our average elevation of just all houses around the world with respect to mean sea level is about 1,325 feet above mean sea level. And then our average global air temperature across all seasons, of course in cold climates it's going to be a lot lower, hotter climates a lot higher, but we'll just say the average global air temperature everywhere across all seasons is 70 degrees Fahrenheit. So we can then calculate the atmospheric pressure once we have the elevation above mean sea level and the air temperature. So we have calculated 0.953 atmospheres using that physical chemistry equation. And then we can multiply that times 14.7 psi at sea level. So at 1,325 feet above mean sea level and 70 degree Fahrenheit air, the atmospheric pressure is 14.0 pounds per square inch. So if we take this atmospheric pressure and multiply it times the molar mass of air, 29 grams per mole, then divide it into the ideal gas law constant for air, 10.73, times the absolute temperature in Rankine, so it's Fahrenheit plus 460, we can quickly calculate the pounds per cubic foot air density. So in this case it is 0.0714 pounds per cubic foot. But whenever we do aerodynamic equations, outside of the metric system, we have to use the slug's absolute mass value. So that is 32.2 pounds mass is equal to 1 slug. So we can divide the air density in pounds per cubic foot into 32.2. So now we have 0.002217 slugs per cubic foot air density at 1325 feet above mean sea level in 70° Fahrenheit air temperature. So next we access the aerodynamic drag equation. So that is C sub D, or the drag coefficient, times rho, which is the air density, times A, which is the projected frontal area in square feet, and then times V, and V is the airspeed, the wind speed in feet per second. So we square that quantity and then take that product on the numerator and then divide it into 2. So that's a derivation of kinetic energy applied to the aerodynamics and fluid mechanics applications. So we're going to test 6 different wind speeds, 25 miles per hour, which is the minimum to obtain a boundary layer. So then the force of the wind becomes the square of the velocity. So we start at 25 miles per hour and then we'll go up to 150 miles per hour. So we can start by converting the miles per hour of the wind into feet per second, and then calculate the drag in pounds force on first the siding at 25 miles per hour. And then we continue on and calculate the wind force on the roof at 25 miles per hour. We add them together and now we have our first value. So at 25 miles per hour, there's already 1.06 tons of wind force exerted against the house in the direction of the wind. So we just repeat the same things across the next 5 wind speeds. And so to speed it up, I'll keep the equation template and we can just change the relevant component or components. So at 50 miles per hour wind speed, we have 4.23 tons of wind force exerted against the house, receiving on the direction of the wind. 75 miles per hour wind speed, 9.54 tons of wind force. Hundred miles per hour, 16.96, almost 17 tons of wind force at 100 miles per hour. At 125 miles per hour, about 26.5 tons of wind force. And then at 150 miles per hour wind speed, 38.14 tons of wind force. So the main takeaway is that the force exerted by airflow at or above 36 feet per second or 25 miles per hour is the square of its velocity. So this represents a typical residential house dimensions. and the average air temperature of 70 degrees Fahrenheit and the average elevation of 1,325 feet above mean sea level. Thank you for watching this video and have a great day.